Hello, everybody, and welcome to Coffee and Smoothie with Chloe in the morning. So I have both coffee and a smoothie with me today. I am going to double check to make sure the stream is working. First things first. Seems like we are good to go. That's awesome. I do have a message to respond to. I'm trying to get the real estate stuff for marmaj set up. So the real estate agent is asking us when we can meet them to look at the property in Antigua, and I'm just going to respond anytime that works. I'm just explaining that we get in the day before, and that as long as, myself and our COO can go visit the property as soon as possible would be great. Okay, so for this stream, I think I have quite a while. I have 11, 12, 1. I have 3 hours to stream if I would like, and so I hope to take up the majority of that time, to be honest. Finish up chapter 2 of this textbook, Cryptography Engineering. I like kind of calling it like practical cryptography because it kind of is trying to help individuals figure out taking cryptography or tools within cryptography and actually bringing them together in a system, practically implementing them. So as you can see, this textbook here is just like a photocopy or a PDF. I'm kind of going through the PDF, taking notes for myself. This textbook's around over 10 years old. And so specifically, when looking at, so I'm doing this for the Ethereum Protocol Fellowship. I'm streaming Mondays, Wednesdays, and Fridays in the mornings if I can. And I'm trying to first pull out information from this textbook that I think is really important for someone who's potentially new to cryptography, whatever their experience is outside of cryptography. They could be a good programmer, they could be a researcher, they could be a mathematician, they could just be a newcomer or someone who uses a VC or someone who uses crypto a lot. Someone who uses cryptocurrencies a lot. Sorry. And so the idea was to first pull out information that could be useful throughout the entire textbook, and then try updating some of the examples and some of the ideas in the text. So one of the main topics is that most of the blockchain-based cryptography libraries are written in Rust, and Rust was not around when this book was written. And so even any of the examples going through the exercises will be all written in other languages. So that's like topic number 1. Go through the textbook, take notes, pull out information we think is important, so that we can formulate it together somewhere else in the future. Also update the information with new examples as I go through the exercises. So Monday, Wednesday, Friday is these streams. Tuesdays and Thursdays, I hope to start doing streams where I go through the exercises. Not yet. Maybe next week, maybe the week after, but soon. So let's just get started. Again, I have my coffee here. I have my smoothie here. My name is Chloe. I am co-founder of the marmaj Foundation. I am the lead of the marmaj Research DAO. And I am currently an Ethereum Protocol Fellow. And my project is probably going to be trying to come up with some sort of new age textbook that helps people work through cryptography engineering. Let's just get started. I'm just going to read through a text and take notes for today. With enough effort, any that's a good place to start. With enough effort, any practical cryptographic system can be attacked successfully. Okay, the real question is how much work does it take to break the system? And that's kind of where the math comes in. That's where usually I've been I'm more used to reading research papers and understanding the math or understanding, how difficult is it to attack this system, and what's the probability that this is secure. And what this textbook is more about is understanding the work it takes, but actually, understand how to build and attack a system. So an easy way to quantify the workload of an attack is to compare it to an exhaustive search. So that seems to be what we're doing here when talking about security level. So seems to be like an easy way to quantify the workload of an attack is to compare it to an exhaustive search. So again, in an exhaustive, well, it goes and explains it right after, which is awesome. I won't try and do it off the top of my head then. Exhaustive search. An exhaustive search. Oh, they even put attack in there to be all fancy and be like, we're specifying that exhaustive attack is one that tries all the possible values. So if you have 2 to the 2, well, here it's saying you have a 235-bit value. So, it 2 to the 235 steps of work. So you have to check every single step. Okay, so an attack that tries all possible values for some target object. In this case, we're talking about keys, mostly, usually, like the key. Like you're looking for the key. Maybe you're trying to get the encryption key, right? As an example. And hopefully that would be clear. Okay. And this is like a super clear example. So if an attack requires 2 to the 235. Whoops. 2 to the 235 steps of work, then this corresponds to an I always want to put anyways, Steve search for a 235-bit value, and it's 2 to the 3. It's 2 to the 235, and then whatever bit value, because bits are 0, 0 or 0, 1, so you gotta search the 2 values, and so it's anyways. We always talk about an attacker needing a certain number of steps, but haven't yet specified what a step is. This is partly laziness, but it also simplifies the analysis. When attacking an encryption function, computing a single encryption of a given message with a given key can be a single step. Sometimes a step is merely looking something up in a table. It varies. But in all situations, a step can be executed by a computer in a very short time. So when trying to define step, let's see if we can, it's kind of awkward to let's just say like this. In all instances, a step, let's just, oh yeah, I checked the stream was working and then I put it away by accident. It wasn't my intention. I do try and, 1 second. Okay, perfect. Good thing I messaged. Let me go back to YouTube. Let me now start writing up what a step is and finish my coffee. I've been so tired recently. And my coffee is very cold. Wow. A step can be oh my gosh, executed by a computer in a very short time. Okay. We are here. Sometimes it can be done in one clock cycle, sometimes it needs a million clock cycles, but in terms of the workloads that cryptographic attacks require, a single factor of a million is not terribly important, which is so crazy to think about when you start like learning number theory and going through what like all those old people from hundreds of years ago had to do. And then looking at now, like, oh yeah, if it's only a million math equations or whatever, it's not that big of a deal for a computer. And it's like, wait, what do you mean? So that's why I kind of like cryptography, because some parts of it always stay the same, like the math, but some parts of it are always changing, like the papers and clock cycles are always a bit different as computers get more important. More powerful. Anyways, the ease of using a single step-based analysis far outweighs the built-in inaccuracies. I like that's probably the reason. So the ease of using a step-based. Like, why are we even talking about steps? Far out built-in. So yeah, steps, trying to define. I should like use tags here, but anyways, I'll try and keep it close together. So even though this isn't the most accurate way of doing things, like the birthday attack, right? It is not the most accurate, but it's close enough and helps us get through the analysis more efficiently, I guess, or quickly. Inaccuracies. I'm having a hard time keeping up with this, like, page. But also, okay, we always talk about step, of using, okay, perfect, that was it, anyways. You can always do a more detailed analysis to find out how much work a step is. For a quick estimate, we can always assume that a single step requires a single clock cycle. I mean, that's... We already... Single step... Single clock cycle. Okay. So single step, a single clock cycle. Okay, I should write that. Just so people understand like how to get started with analysis and reading papers too. Any system designed today really needs at least, okay, so this was right 10 years ago, right? Take everything here with a grain of salt. So any system designed today needs at least 128-bit security level. So now we're talking about security level. It should mean that you gotta do at least 102 to the 128 steps, right? Clock cycles to be able to break encryption. Again, take it with a grain of salt. That was 10 years ago, 12 years ago. That means that any attack will require at least 2 to the 128 steps. A new system designed today is, if successful, quite likely to still be in operation 30 years from now, and should provide at least 20 years of confidentiality for the data after the point at which it was last used. So we should aim to provide security for the next 50 years. So should aim to build for the next 50 years of use. I'm going to try and, as I go, and take less word for word what the text is saying, and try and, as I understand what I'm trying to work on more write in my own words, and try and figure out like what paragraphs might look like and all of that. That's kind of why I'm also trying to do full sentences and just take things. But yeah. Okay, that means that any attack will require that many steps. Okay, 50 years. That is a rather tall order, but there has been some work done to extrapolate Moore's law and apply it to cryptography. A security level of 128 bits is sufficient. One could potentially argue for 100 bits or even 110 bits, but cryptographic primitives are often engineered around powers of 2. So we use 128 bits. So I mean that might be something that could be useful. Like primitives are often engineered around powers of 2. In my opinion, this is, again, I don't want to like write it down. I don't know nothing. But in my opinion, this is because computers are able to like compute on those powers quickly, right? So like I know like some newer algorithms are like specifically made for like 64-bit encryption, or like 30, whatever, like, or like messages or whatever. I don't know, but these days there's so many different algorithms that like it could take a whole 4 months just to learn, like really get in the weeds of one algorithm. And I kind of don't want to use this time for that, because I could easily do that. I want to kind of use the next 4 months to get a more higher level view, to bring more people into where that is, but then also maybe pick, yes, of course, a couple projects. So right now the project is VAC P2P. They have like a project and they're looking for a Rust implementation. So that's like a long-term project I would like to work on. But for now, this is kind of where I'm at. This concept of security level is only approximate. So that's like obvious, but again, this concept of security level is only approximate. We only measure the amount of work the attacker has to do, and ignore things like memory or interactions with the fielded systems. The fielded system. Dealing only with the attacker's workload is hard enough. Complicating the model would make the security analysts much harder still, and greatly increase the chance of overlooking a vital point. As the cost for using a simple and conservative approach is relatively low, we use the simple concept of security level. So basically, security level is only approximate, but it helps you get a quick and generally, vaguely accurate assumption of the security of a system, which can help you kind of ensure that you have at least a certain amount of security and move quick enough to build. It would kind of just be too expensive and take too long to do a full analysis, I guess is the point. It's hard enough to do this. The level of security is, however, a function of the access of the adversary. Is the adversary restricted to the known plaintext model, or can she operate under the chosen plaintext model? And how many encrypted messages can she see as part of her attack? I think the main part there, of course, is the level of security. Like in actuality, is a function of the access of the adversary. So you can like try and assess your system, like, oh, the adversary should have to do this much work, but it's really a function of how much power the adversary has. So generally you have to like write out, okay, so this is how much security, or this is the security level of our system, so the attacker has to do this much work, but that's based on the attacker having this much power. So you kind of like, usually if you're writing a paper or something, you would define how much power the attacker had, and then write, okay, when the attacker has this much power, this is our security level. When the attacker has this much power, this is our security level. And then you kind of just go through the different levels of power, showing, you know, how secure your protocol is based on each security level. Okay. 2.9 before, oh gosh, caps lock. So yeah, Obsidian, the text editor I'm using now, apparently is way more powerful than what I'm using it for. I will get there eventually. I try and use my weekends for like extra learning, like how to use Obsidian more efficiently, how to use VS Code more efficiently, how to learn Bash scripting more efficiently, like all that type of extra stuff. And I really am trying, because I mean, there's so much marmaj Foundation stuff to do on a weekly basis. I'm realizing that if I don't take Monday to Friday and just fully focus on Ethereum fellowship stuff, I just won't get through it. So security does not come for free. That seems like a fine enough. It's a bit too obvious maybe, so maybe we'll add more. While cryptographers do try and make cryptographic algorithms as efficient as possible, these algorithms are sometimes perceived as being too slow. No, that's not. Cryptographers try and make crypto algos as efficient as possible. Yeah, I'm definitely gonna start shortening a lot of words just to make a lot of this hopefully go a bit faster. Algos still sometimes deemed, sometimes perceived too slow. I do like the word perceived because maybe they're not too slow, but the users or the company might seem too slow or whatever. Creating custom cryptography for efficiency can be very risky. You know, custom crypto for can be risky. So I think these days they call it like rolling your own crypto, like setting up your own system. But I think that's the point of what I think this project is about. Is yes, it can be risky, but how do we get together teams that can roll their own crypto? If that's the word that's used. I'm going to use the word creating, obviously. But yeah, anyway, let's continue. If you deviate from the beaten path in security, you have to do an enormous amount of analysis work to make sure you don't accidentally end up creating a weak system. So I think that's the point. It can be very risky, but why is it risky? You have to do an enormous amount of analysis. You know, from experienced cryptographers. You have to know also to ensure you don't accidentally create. I mean, I think the point here is that you're trying to roll your own crypto. They need to go hire experienced cryptographers to like analyze your system, take all this time and make sure everything's, you know, working all right, which can be very expensive. Which I think is like where we're at in like the current blockchain space. Is like blockchain teams are getting funding to roll their, to like create their own crypto systems and like analyze them and like get I think the idea is blockchains allow us to fund all of this public research. Like, finally, this stuff is funded. I don't know. It's insane to think about. That's why I love learning it. So this is what I do. I love learning this stuff because it's funded. It means that there's communities built around it now. There's resources to support. I'm trying to create resources. If someone like me is trying to create resources for this, how many other more reputable people are doing the same? That's kind of how I see it. And so if those people are also creating resources, I can learn from them. Is the goal. Security does not come for free, blah, blah, blah. Yeah, we don't really care about cost. I guess I'll just put, like, very expensive. But the idea is that, again, I think that's the main inhibitor. But if you can get around that inhibitor, it seems relatively reasonable if you can get the analysis and everything else. So go for it, for efficiency's sake. For most systems, the performance of the cryptography is not a problem. Modern CPUs, for most systems, the performance of the crypto is not an issue, since it takes longer for pages to load. So modern CPUs are so fast that they can keep up with almost any data stream they handle. For example, encrypting 100 megabytes per second data link with the AES algorithm requires only 20% of the cycles on a 1 gigahertz Pentium 3 CPU. Okay, so this one's talking about the CPU. Since modern CPUs are so fast. I like that so fast thing. Modern CPUs are fast enough to handle most data streams. And they gave an example. Okay, less in real life, you never get to transfer 100 megabytes per second over such a link due to the overhead of the communication protocol. There are, however, some situations in which cryptography creates a performance bottleneck. A good example is web servers that use a very large number of SSL connections. The initialization of an SSL connection uses public key cryptography and requires a large amount of computing power on the server side. Instead of developing a custom SSL replacement that is more efficient for the server, it is far cheaper and safer to buy hardware accelerators to handle the existing SSL protocol. And then, so for most so even in systems where crypto is a bottleneck, cheaper to buy hardware accelerators, right? So the idea is, even with SSL, they're saying this is one example where, they could try and develop more efficient crypto, but it's safer to just accelerate the hardware and, make the servers more efficient, which, recently ran across a good argument to convince people to choose security over performance. There are already enough insecure fast systems. We don't need another one. This is very true. Half measures in security cost nearly as much as doing it well, but provide very little practical security. We firmly believe that if you're going to implement security, you should do it well. Yeah, I mean, that's probably, hopefully, an obvious point, but you never know. complexity. So first talk about performance, like how do you know what's the security level of your system? How do you know how it's performing? Security doesn't come for free. How do you balance between security and efficiency? And then now complexity. This one's relatively straightforward. The more complex a system is, the more likely it has security problems. Okay, sorry, I've not been having my coffee. It's a simple statement. Took them a while to understand it. For me, as someone who's not a very good programmer, I understand it, in my opinion, instantly, because like there's just so many levels to this. Even, let's say, a system's very complex and very secure cryptographically, and then the maintainer passes away, sadly, or runs away, or just gets sick, or doesn't want to deal with the code anymore. The inability for the community to easily update code base, that could be an issue with security. Like, there's just so many ways this works. But anyways, part of the problem is the test and fix development process used all too frequently. Build something, test for errors, go back and fix the errors, test to find more errors, etc. Test, fix, repeat. This goes on until company finances or other factors dictate that the product be shipped. Sure, the result is something that works reasonably well, as long as it is used only for the things that it was tested for. So, part of the problem is, this test and fix, oh my gosh, this test and fix development style only works well for the things it was tested for. Well, yeah. This might be good enough for functionality, so might be good enough for functionality, not for security. I think that's the idea, is that when you have a system where one person breaking in one time breaks the whole thing, it's very different than have a system where when 1,000 people breaking a web page might not be a big deal, but one person breaking a cryptographic system could destroy the entire system. So, but not for security system. The problem with the test and fix method is that testing only shows the presence of errors, and really only those errors the testers were looking for. Security systems have to work even when under attack by clever, malicious people. The system cannot be tested for all situations to which the attackers will expose the system. So, the system cannot be tested for all possible attacks from malicious. Just to be very clear, someone's malicious and clever. Let's even be more clear. This person's clever and malicious, and you can't think of every single possible test to get around someone like that. So how do you still build a safe system then? The system has to be secure from the start. Okay. Consider the following analogy. Suppose you write a medium-sized application in a popular programming language. You fix the syntax errors until it compiles the first time. Then, without further testing, you put it in a box and ship it to the customer. What? Nobody would expect to get a functional product that way. Yet, this is exactly what is normally done for security systems. They're impossible to test because nobody knows what to test for. By definition, an attacker wins by finding any aspect that wasn't tested. Let's put that one, I mean, any, just at least one, greater than equal. Ooh, maybe I should practice my greater than equal to, because I haven't done it in like years. Oh gosh, first time doing greater than equal to in a while, but I definitely have to practice something like that. That's a simple one. There you go. Where's the next one? No, greater and equal. Greater and equal. Okay. So we're seeing greater. Ugh. That's annoying. Maybe I can just Google it. So greater equal latex right there. Greater than with complete equal to sign. That should work right here. Attacking fingers by greater equal to. Oh, it needs to go between the little blah blahs. Okay. Yeah, literally needs to find just one. That wasn't tested. Okay. Oh, yeah, I knew. Okay. And if oh yeah, you can't test because no one knows what to test for. The attacker wins by finding any aspect that wasn't tested. And if there's any bug, the product is defective. So the only way to get a secure system is to build a variable system from the ground up. This requires a simple system. The only way we know of making a system simple is to modularize it. Only way to make a system simple is to, well, okay. I did not spell that right. I already knew I didn't spell that right. Oh my gosh. It's probably a word that this, okay, so I'm gonna have to actually look at the screen. It's because like I can't highlight the word, so my brain has a hard time looking at a word within all these words. And anyways, modularize. Now I gotta save the word and modularize it. Well, I don't want to say the only way because they're saying the only way we know. Okay, so the only way. Oh gosh. I'll use that. Like, I don't like that either. But the authors are writing this, right? Saying they don't know any other way. And so I don't want to write something as fact if I don't know. They're saying. We all know this from software. Like, we all know this. They're saying it's a fact, but still. We all know this from software development. But this time, we cannot afford any bugs at all. So I'm just gonna be like that, and then be like, this is known. Oh my gosh. This is generally known from software dev, but oh gosh. But with crypto systems, no bugs allowed at all. Sure. Or just no bugs afforded. Quite ruthless in the modularization. This leads us to another rule. Correctness must be a local property. Let's see. In other words, one part of the system should behave correctly regardless of how the rest of the system works. So, one part of the system should behave correctly, regardless of how the rest of the system works. So he's operating. So basically, if one part of the system, everything's being simple and modularized, but if one part of this broken apart modularized system fails, everything still works. I mean, as a human being, that's kind of how we work for the most part, right? Cut off your hand, which is a pretty important part of your body for protection and defense and support and doing things, but your body still works. The system doesn't break down because your hand. And there's so many attacks to the human body that we probably couldn't even think of. But again, the body just thinks of new ways to defend itself, and I think the body is a great way of looking at a lot of software systems, to be fair. Okay, no, we don't want to hear this won't be a problem because this other part of the system will never let this happen. The other part may have a bug or may change in some future version. Each part of the system is responsible for its own functionality. Finally, we finished it. So I think it's chapter 3. But first things first, let's go over to the exercises. I do have a lot more of them written out, but I don't think I had... Oh, I already did it too. So for chapter 2, let's try and go through them quickly, potentially. I'm not sure if I really want to go through them yet, but... So consider Kirchhoff's principle. Provide at least 2 arguments in favor and at least 2 arguments against. Then state and argue your view of the validity of Kirchhoff's principle. I can't remember Kirchhoff's principle. I have the note for it somewhere, but I think the quickest thing to do is just Google it quickly. So yeah, a crypto system should be designed to be secure, even if all its details, except for the key, are publicly known. So they didn't actually label it that well in the textbook, actually. I think this is actually a really great way of putting it. So I'm actually going to take the wiki link and add it to just the question, because I think that'll help people answer the question. Because that makes it pretty obvious, especially when you get to chapter the end, where it's like, okay, modularize your system, everything should work. Even if someone attacks one part, everything else should be safe. So I mean, okay, so to me, this is an obvious one. I don't think we need multiple in favor or against. Sorry. Okay, designing your system, assuming that your opponents know it in detail. Okay. Obviously, I don't know how you say anything against this, especially now that we have like public blockchains where we want everything to be public except for the key, and we want the system. We want the ability for someone, especially in like near or some of these like blockchains that have multiple keys. We even want people to be like trade their keys and burn their keys, and I mean a lot of systems are like this, but where everything's supposed to be public, I think that's an obvious one. Yeah, I don't like. That's one that I think it's kind of like I don't need to. But I want to add this. I don't think I need to answer the question. Suppose Alice and Bob are sending emails to each other over the internet from laptops connected to free Wi-Fi. List all the parties who might be able to attack this system and what they might be able to accomplish. So listing all, I think, is a great exercise. For me, just let's just be really simple. Obviously, the actual coffee shop or wherever they are might be able to attack the actual like system and attack like Alice and Bob and view what they're doing. Anyone else on the free Wi-Fi will be able to listen in and see at least what's happening. They could be able to stop them from being able to get Wi-Fi or like delay packets and stuff. So there's lots of and it depends what system is being used and how much power an attacker has. Like, is the attacker actually the coffee shop? Is the attacker the internet service provider? Is the attacker like some other person in the shop? So again, that's like all these different things and reasons and like all this stuff. There could be a whole paper about how to defend yourself from things in a coffee shop. So same thing here. How you might defend against some of these attacks. Like maybe just use a VPN, or maybe you so you're connected to free Wi-Fi, sending emails. Maybe you encrypt your message, and you're both in the coffee shop together, so you can like send a piece of paper with like the key, right, and message back and forth, yada yada yada. Lots of ways to use encryption, for example, that we learned in Chapter 2 to be able to send messages back and forth. Very straightforward. Consider a group of 30 people who wish to establish pairwise... Oh, did I already do this on the call? Maybe I did. So basically, it's just like 30 times 29 divided by n, I think. So 30, I think. So let me do it again. I think it's 30 multiplied by 29 divided by 30? No. 2? Yeah, there you go. Sorry, divided by 2. Yeah, so it's like n multiplied by n minus 1 divided by 2 is how that works. It's the actual equation. I should probably write out the equation for that one too. Right, so it ends up being n by n minus 1 over 2. Oh, one more bracket. Okay, so suppose Bob receives a message signed using a digital signature screen with Alice's secret signing key. Does it prove that Alice saw the message and chose to sign? No, we went over this. Keys are, no. Keys are, let's just maybe, key. Secret signing key. So this is like the authentication key, I guess. Maybe, I think so. Is long and difficult to remember, so computer does the signing. Malicious party could have taken over Alice's PC and signed. Let's just keep it like that for now. Suppose that a private key infrastructure do not exist. Suppose Alice obtains a public key P that purportedly belongs to Bob. How can Alice develop confidence that P really belongs to Bob? Consider the following. So these to me seem a little silly, but again, I'm assuming they're saying the phone is a secure connection. I'm going to assume. So if Alice and Bob can talk over the phone, if you want to know that P actually belongs to Bob, you can go through like the message sending setups above. And if you need a secret key, I mean, technically, you can send the secret key to Bob over the phone if we're assuming the phone is a secure connection. If not, then I'm sure we could use another piece of data, or because you already know the public key belongs to Bob. Sorry, so if you send a message, Bob should be the only one able to receive it. Ugh, am I gonna have to go all the way back up to? Anyways, Alice can talk with someone else she trusts over the phone, and they've already verified that P belongs to Bob. Alice can communicate with Charlie via email, so I'm assuming we're saying email is not secure communication. And Charlie has already verified that P belongs to Bob. But I'm assuming here we could just use, again, some sort of message that proves. Ugh, I feel like I'm gonna have to go back to like look at the actual way he wrote it out. Here we go. So we're talking about a digital signature, and okay, so you have, Bob has a public key and a private key, and you're trying to verify that Bob's public key is valid. So you got to send over a message and Alice's signature. So again, if you could talk to Bob over the phone, I would assume you'd be able to send over the message at least, and I guess maybe even the signature over the phone, maybe, right? Because the message should be simple enough. So Bob uses the public key of Alice. Oh, no, you just ask Bob to send you a message and you try and decrypt it, right? If Bob sends you a message and a signature over the phone, you could decrypt it if Bob is actually Bob. So, because anyone can know that Bob is actually Bob. If Alice can talk to someone else, but not Bob, so you can't get the message directly from Bob. But again, I'm kind of maybe a little confused. Again, maybe I'm wrong, right? So don't take my word for it. But I assume that if anyone, and they have already verified that P belongs to Bob. So yeah, in my opinion, if Charlie has received a message from Bob, knows that Bob is correct, I'm assuming that then Charlie can send a message to Alice with some sort of cryptography proving that Bob is Bob. And if Charlie's, she trusts Charlie over the phone, so Charlie can do the same thing, the message and the signature proving Bob. And then if you can communicate over email, I'm guessing to me, I don't know actually. Oh yeah, that's why, I don't know why it keeps not changing that. This was the one where I didn't understand, like, why it changes it from email to the phone. Are we saying the email is easier because you can just copy and paste these things? Are we saying that email is less secure, which is what I would think maybe? But yeah, anyways. Not actually sure. That's why we're having a study group and not just me teaching. Suppose a chosen ciphertext attacker cannot recover the secret decryption key for an encryption scheme. Does this mean the encryption scheme is secure? I'm just going to put one no answer. So no, the attacker may be able to, like, let's just say even delay messages, right? Because you need the secret key to decrypt the message, but if we go to chosen ciphertext, here, so in this attack, you get to choose the plain text and the ciphertext values, and so if you're able to, and then your goal is to get the key. So it's saying if you're using this plaintext model and your goal is to get the key and you're not able to get the key, you know, is it safe? And then, in my opinion, anyways, there are times I put no, saying it's not safe because if you're able to choose the message, just because you can't recover the key doesn't mean you can't learn. Okay, yeah, I'll keep it simple as possible, my answer. Gain other info about the message, first bit, which could still help the attacker gain important info. Keep it super simple. I don't want to, again, for now, don't want to be going into too much detail about these answers. Just keeping the answers like straightforward and simple. And then 2.7, consider a symmetric key system. Oh gosh, a symmetric key crypto system, which means you use the same key to encrypt and decrypt. And if someone finds that key, all messages are screwed. Yeah, anyways. But you can use other information to... Anyways, doesn't matter. In which cryptographic keys are randomly selected from the set of all n-bit strings. Approximately what should n be in order to provide 128 bits of security against a birthday attack? Honestly, it's just n divided by 2. Yeah, and we can go back to the birthday attack. Like if I, and we could talk about how, a fresh 64-bit authentication key, after about 2 to the 32 transactions. It's not actually half, of course. It's not, the number 2 to the 64 is not twice the number 2 to the 32, okay? But I'm just saying, like, if you're just trying to do the exercise, trying to understand what's happening, it's... yeah, it's just it happens sooner than you think, and yada yada yada. But okay, now we're going on to chapter 3. So part 2. Okay, so we got through this today. So I should actually part 2. Message security. I will probably do a little this part type of thing, because I would love to do it like this, or how do I do it? Yeah. Wait. Darn it. Either way, it doesn't work on Discord, so it's kind of annoying. Do I have to use like a tag? Oh. Tag to something within the doc. In this part, chapter 3, block ciphers. Chapter 4, block cipher modes. Chapter 5, hash functions. This is all pretty straightforward stuff, it seems. Oh, chapter. Actually, is it saying that I have Near DAO Demo Day, or it's just the wrong account? Okay, I'm still not drinking my coffee much, but Okay, so we go back through max, so which is good because we'll actually dig into them in more detail. I don't know why there's an I there, but maybe it's the first one and they have another implementation issues section. Either way, we actually get into chapter 3. Now I'm going to forget how I did it for chapter 2. What? Oh, I didn't even do a proper, like... Ugh. Sorry, that's going to bother me. I've got to do a proper, like... What did I do for part 1? See, this is how I bother myself. Did I really do that? Okay, sorry. Let me just do some editing here. So, part 1. Now I'm already forgetting how I did part 2. Okay, so part 1. Introduction. And then in this part. What did I do last time? See, this is me just not remembering. Okay, I did it right below and then... part. Because then I can put like links, right? And link throughout the... If someone doesn't want to actually read something, they can know what's happening. Introduction to cryptography. Oh gosh, context. Why are there so many? Oh, because this one I did on HackMD. Yeah, you can see the difference there for sure. Okay, so we have introduction in this part. You have these two things. Oh, I didn't even do this properly. Right. So it should be like... That's fine. But what did I do for chapter 2? I must have written it differently, knowing myself. Ha! See? I didn't even do it properly here. This is me just not thinking when I'm doing things. So let's fix this too. Oh my gosh. CH2, introduction. Introduction to cryptography. This one had an actual... Ah, this one actually links. Perfect. So I should have done this for the other ones. Oh no, this is linking to... wrong thing. It's not linking to... I meant to link it to... Okay. I meant to link it to GitHub, I think. So let me do that now. For chapter 1. Just to keep it super simple, like linking it to Obsidian for now is great for me, but not for others. Okay. Okay. Sorry, I'm just looking through things. close my thing again. Okay. No, it's not the weekly updates. It's the EPS, it's notebooks, and it's the exercises. Okay. Now, chapter 2, introduction. We go through 2.1. We get to the end, 2.9, 2.10. And then I should do .11. And what did I write here? My gosh, my memory is... I really liked how I had it at the end. General exercises. Let's see what it says here. If that's what they call it. Nope, it is called exercises. Now I'm going to have to... Oh, they did call it general exercises, and this one they called it exercises. Okay. If that's what you want. Exercises. Which would link to... Oh my gosh. Okay. I can just write here chapter 2 exercises. Sure. Because GitHub should allow me to go here and then get a link to chapter 2. Right? Sorry, that was unnecessary. There you go. And then chapter 3. We could finally start making notes. Okay, so chapter 3 is trying to talk about did I do? Okay, now I'm being a bit wild, right? Fine. It won't give me 3, eh? Okay, chapter 3. Page 3. I get OCD if everything doesn't look the same. So block ciphers are one of the fundamental building blocks for cryptographic systems. There's a lot of literature on block ciphers, and they are among the best understood parts of cryptography. They are, however, building blocks. For most applications, you probably don't want to use a block cipher directly. Instead, you'll want to use a block cipher in what's called a mode of operation, which we'll discuss in subsequent chapters. This chapter is designed to give you a firmer understanding of block ciphers, what they are, how cryptographers view them, and how to choose between different options. Okay, so block ciphers are one of the fundamental building blocks for crypto systems. Yeah, honestly, it's pretty clear with just the one sentence what's happening here. So now we're going to go through block ciphers a bit. So what is a block cipher? Probably one of the good first point to go through. So 3.1, what is a block? And then after I go through this entire book, to be honest, I'm going to go through a lot of this on Wikipedia and see, like, yes, this is what was written before, and these are all the topics, but what are the current, resources on each of these topics, and then what are the Rust resources on these topics. But for now, just going through the topics. So a block cipher is an encryption function for 6 fixed size blocks of data. An encryption function for fixed size blocks of data. Simple enough, hopefully, since we've gone through encryption before, we've gone through encryption functions, and so now we're just saying that all of the data going into this function is of fixed size. The current generation of block ciphers has a block size of 100 and so current generation of block ciphers, again with a grain of salt please, because this was written 12 years ago. Block size of 128 bits, so 16 bytes. Hopefully that's simple enough. These block ciphers encrypt a 128-bit plain text and generate, so what that means is they're encrypt 128-bit plain text, and generate 128-bit cipher text. Okay. The block cipher is reversible. So block cipher is reversible. So there's a decryption function that takes the there is a decryption function that takes the 128-bit cipher text to plain text. Okay. Block cipher. Ooh. Yeah, sorry. Cipher text to plain text. So basically, this block cipher takes fixed size blocks of data, puts them, puts plain text through an encryption function and gives you cipher text. And then there's a decryption function that takes the ciphertext and decrypts it back to plain text. So that part should be straightforward enough. The plain text and ciphertext are always the same size. That, I guess, should also be relatively straightforward. So plain text and ciphertext are always the same size, just generally. I gotta stop doing that. Fine. We call this the block size, which is the block size. To encrypt with a block cipher, we need a secret key. Without a secret key, there's no way to hide the message. Like the plain text and ciphertext, the key is also a string of bits. So, like the plain text and ciphertext, the secret key is also a string of bits. So this is kind of where I was getting confused when I was going through some of this stuff myself. So on VS Code, I have a little thing here where I'm using OpenSSL, AES. So AES is a type of cryptography, which we'll go through in chapter 3. So you have your key here. This is just an example I took directly from the internet. So you have your key in hex here. You have your plain text in hex here, a string of bytes. So again, you have your IV, which always confuses me a bit, but this is a bit newer from the text. It's like a random string that like increments. So normally you'd want to change your IV each time you're encrypting or decrypting, I guess. Or the IV is the same for encryption and decryption, but you want to increment it or change it each time. So then you, I guess, I think this is just me and like Rust. I'm not understanding. To me, it seems like key is not mutable or something, and then here all of a sudden, like, you know, you just let key equal, and then you like go into AES, and then you do a new encryption of the key, which is here, or I guess you get a new encrypt key and you unwrap it. My understanding is to actually get what it returns is you unwrap it, and then you know it's not going to fail, so that's no error handling. That's fine. Again, I'm not amazing at Rust. This is my understanding. Now you do want the output to be mutable. So I don't know why there's a zero. Interesting. So the 0 is what's in front. Oh no, it's just highlighting numbers. Anyways, the output. Where's output? Oh, output. What does output take in? Let mute output equal these two things. So you're going to take in that. Oh, so this function up here takes in the plain text, a reference to the mutable output, which I guess is what we're going to get here, which we just set up. We set up the, I'm not sure what that's called, the variable for, a reference to the key, which I guess has been changed here. So we're talking about this key now, which is a new AES key, a reference, a mutable reference to IV. Oh, it's already mutable. So yes, I guess IV changes. I guess because you might increment it. I'm not even sure. A reference to a string of bytes. And then our mode is encrypt, because we're gonna, encrypt. And then this is actually the one statement that I'm a bit confused on. I guess what I should probably do is like, and I probably don't even know how to do this, but like, let's see if I can do this quickly. Oh no, it should be simple, right? So, no. Print. Isn't that how you do it in Rust? Man, I can't remember. I'm just gonna Google it. Print in Rust. There you go. But why don't I have the autocomplete thing on in here? Much simpler if I had that. Print ln output. That's all I know how to do. Cargo checked failed. I don't know, like, honestly, I just set this up. My workspace is not fixed yet. I'm just gonna, like, I have no clue. But I will open my terminal. I will CDA, oops, CDA, let's clear some of this, encrypt, so CD encrypt ls, okay, I think I could cargo build now, no, okay, Cannot be formatted with default error. Oh. Oh, because output needs to be U8 and this. Oh, because this is going to try and print a string. Let's see. Use of an undeclared crate or module, open SSL. Target, debug. Oh. Sorry. Here it is. I don't know why this wasn't already in there. So let's try this again without changing anything. I'm not sure it'll work, but okay. I think I was looking at the same error, but at least now it's trying to build because I have the right package. I still think I might have an error in main when I'm trying to print the output. I haven't really dealt with the bytes. Cargo version failed? Like, that's weird, right? Maybe I should check my cargo version. Yeah, so U8 16, like cannot be formatted with the default formatter. Help. The trait is not implemented for this in the formatted string be able to use for pretty print instead. Okay, yeah. I literally might need both. So honestly, I'm not good at like understanding this. I know it's like for more general input, but still, it's not my cargo build. Oh, let's look at built. Cargo run. Okay. So now we're printing out the bytes in numbers instead of. Okay, so let's try this again. Because I don't know what the heck's going on in any of this. So I'm just going to try and say print the key, because I don't even know what the heck's happening with this key. And then let's see what we get. Cargo build. Oh, it worked. Cargo run. Okay, so this is where I'm getting confused, because this is where what I'm seeing anyways, is that we're putting in a key, a plain text, right? I'm assuming this is the plain. No, wait. Sorry. Let me fix this. Let key print out. Key is print. Sorry, this is me. Print plain text is. So this is hopefully going to help me a little bit to actually see the numbers. Let's try this. This might work. And sorry, I use my terminal to build these things instead of using VS Code. I don't know. Cargo build. So usually I do this Tuesdays and Thursdays. I should not be doing this today. I should be reading, but I couldn't get this yesterday. So cargo run. Okay, so I'm not understanding, in my opinion. So it seems to me like the key is the same as the plain text, and then we're encrypting it, and maybe this is the encryption, and we haven't even done the decryption. So the key is just 1, 2, 3, 5. You can use the key to decrypt. So I guess I would have to then, you know, come in here and then like I think this is just telling me how to encrypt something. And then I think I could take this output, which is this, apparently. Same mute IV. Same key. Different plain text. Okay, I'm a little confused, but I'm going to try something that might unconfuse me, because I would assume that potentially could comment out this line, keep the same mute IV, comment out the plain text, have to use the same key. So what I would assume I'd be able to do is copy, sorry, we're just copying the bytes. Let's copy it from inside the quotation marks. And so I would assume that we could change the plain text to being the output. Okay. I would so okay, everything the same. So far we're starting this, you know, Rust thingy. The key is the same. We're gonna print out that key. The plain text has now switched to being the previous output. So plain text, we're gonna print it out. Mute IV is gonna stay the same, right? When we encrypt and decrypt, we don't want to change the mute IV. Sorry, the IV. Sorry, it's mutable. Oh gosh. So we're still gonna do the same thing, except this time we are going to, I assume, again, just going to new decrypt key. You're going to have the same output. You're going to take all this, instead of encrypting, decrypt. Again, I haven't checked the actual function. I could go check it. It's saying something's wrong so far. So what is it not liking? Let plain text equals. Oh no, it's just showing me changes, I guess. Deletions, sorry. Okay, so you still get the same mute output. You call the same function with all these parameters. The plain text is up there. The output is right here. The key we still have. The IV is the same, and we're changing the mode. And then we're going to print out this output, which should be, I actually don't know. We'll see. We'll play with it. Cargo. Let's see if it builds with my changes. No. Okay. So yeah, I did. Oh, sorry. I didn't see the. Now it should be okay. Let's try now. Cargo. Okay. Yay! It built. And okay. So. Okay. So the key, I think we rebuilt this, right? So okay. I used the new plain text, which ended up equaling the previous plain text, right? So Last time I was able to put a key and the plain text and get this. Okay. And then I went so the output is different, right? Which is the actual, yeah. But this plain text, it seems, was the same as this one. So I think I did it correctly both times I did it. Let's double check again. So the previous time I did it, I put the key here, the plain text here, and I got this output. And I put the key here to decrypt, and I got this output. So I'm assuming that's correct, because it would be deterministic, where I was able to encrypt and decrypt, and then get, I think I'm supposed to get a different result. I think the same result would be bad. But again, this is the area where I need to make sure I understand what's happening. But that was one of the library here, so you can go on the GitHub and click into that if you'd like. Using the library, decrypt the following ciphertext. So this is actually what I should be trying to do after I go, so not today, I'll do this on probably Tuesday of next week. But the idea would be here now, whoops, to be able to take whatever hex I wanted. So it's saying, using this, we're going to have the ciphertext, right? And we're going to decrypt it, because this is ciphertext. So what I would do, I think, okay, now this is going to take a lot out of me, because I have it here with like the X's in front, and I'd have to change those out. But we have, oh shoot, it should be called ciphertext if we're decrypting. So I'm just going to call this ciphertext, and I'm going to call it, oops, I want to get actually a new one. So I forgot all the commands to like create new line underneath, create new line above. I haven't used VS Code in years. I used to use Vim, so, and I forgot how to use Vim too. So currently it's in a decrypt setting already. So let's just, whoops, keep it how it is. We want ciphertext mode decrypt. This one is mode encrypt. We have print line output, and this whole assert equal, I'm not actually sure how to use that at the moment. So I'm just printing the output of the, this is actually what I want to know more about. Like, how do you even figure out what the output's supposed to be, then assert it to equal? It seems simpler to me to just be like, okay, print out the output and then try and encrypt and decrypt and see if you can do both. So I made a file called encrypt. I should have a file called decrypt, and then I can just go back and forth. But for now, I'm just going to literally change the values. So normally what I would do is I would take the ciphertext here, and I would change it for the bytes here. So hopefully that part's clear. The key here would go for the key here. The mute IV would stay the same for encrypting and decrypting, and then this is just what you go through. The next question, question 9, is using an existing cryptographic library, encrypt the following plain text in hex. So again, you would change these out. You would use plain text and switch it out here. You would take the key, and again, you would encrypt it using this key, using AES. And so hopefully that's clear about how you would actually start using some of these tools. Again, I copied this code directly from the docs, right? IES, IGE, took this code, copy and pasted it. They do have the key wrapping, which we'll talk about in later chapters. Let's get back to the notes. Awesome. But I just wanted to kind of like shore that up from last week and get further along, even though we do have a bit further to go. Did I just start going and do a huge tangent? I did do a huge tangent. Nice. So let's get back from my huge tangent. Cute. My wife sent me a nice Halloween costume idea for Naruto, and I'm down. Yeah, sounds good. I'm just gonna respond to her real quick and be like, yeah, sounds good, let's do it. It's an easy costume. Okay, so I'm getting a little tired. I still have to finish my coffee and drink my smoothie and probably get a second wind soon. And I think I have until quite a bit of time. Until 1. So I'm definitely not going to stop that soon. I'm going to just continue going. I definitely want to get a bit into Chapter 3, especially the easy stuff, until we get into like a lot more complex stuff in Chapter 3 and 4. So we went through what a block cipher was. To encrypt with a block cipher, we need a secret key. Without a secret key, there's no way to hide the message, like the plain text. Secret bits, common sizes are, 128 and 256 bits. Commonly 128 and 256 bits. Written as the encryption, encryption of, I'm having a hard time today, K with P, or the encryption of K for P. For the encryption of plain text, hopefully that's clear, with key, hopefully that's clear, and obviously we have the other way around, so I'm just gonna copy and paste that. Oh my gosh, it doesn't want to copy and paste, and just change out the D. And the D, we're talking about encryption and decryption. Oh, sorry. Shit. Ciphertext. So, decryption is always using ciphertext. So, actually, I was going through some of the libraries online, and I think some of the newer libraries might use ciphertext more often. But anyways, because of the block mode or cipher block modes. But anyways, mostly information. For security purposes, however, one rarely uses a block cipher directly. Instead, one should use a block cipher mode, which is discussed in Chapter 4. Okay. Block ciphers should... This is actually what took me a while to understand. Always be used, should use a block Well, instead of using block cipher directly, one should use a block cipher mode, which apparently we're not going to define. I wish they just defined it quickly, but again, I'll just write, you know, if someone wants to know, it's ch4. When using block ciphers, as with any encryption task, we always follow Kirchhoff's principle and assume that the algorithms for encryption and decryption are publicly known. Some people have a hard time accepting this, and they want to keep the algorithm secret. Don't ever trust a secret block cipher. That's, I like that one. Don't ever trust a secret block cipher. That's simple enough. These things should be public. We should know what they are, the algorithms, and we should be able to ensure or, you know, prove security or a security level, even if the algorithm's known and someone only has their private key safe. They should still have security. Okay, it is sometimes useful. It is sometimes useful to look at a block cipher as a very big key-dependent table. For any fixed key, let's put that. Can be useful to look at a block cipher like a very large key-dependent table. For any fixed key, you could compute a lookup table that maps the plain text to the ciphertext. This table would be huge. A block cipher. Okay, I like to do a little math. For any fixed key, the table would map the plain text to the cipher text. Hopefully that's a very like a visual, like a visualization, a good visualization of what like the block cipher kind of looks like. You know, table would be huge, specifically for a cipher with 32-bit block size. Table would, you know, 16 gigabit table. 64-bit block size. Oh gosh, it shows you how exponentially it grows. Million TB, and then as we get bigger, 128-bit block size. Put my table in a little bit. Ooh, I forgot how to do a little dot in the middle. Maybe I should memorize that. Get that one down next. Let's do it. Gosh. Wow. Imagine it's just a dot. I don't want an X. I want a dot. There we go. Give me a dot. Okay, C dot. Yes. Okay, 3 C dot. I knew that. So we would say 5 C dot. Is it gonna like it? 10 to the power of 39. Nope. It needs. Oh, it did work. Wow, that's cool. No, it needs the other way. There we go. Haha, got it. Bytes. Crazy, right? Of course, it is not practical to build such a table in reality, which is why exhaustive search is not realistic. But this is a useful conceptual model. We also know that the block cipher is reversible. In other words, no two entries of the table are the same. So it's a lookup table or whatever with potentially this many values. It's so many values you can't even imagine them, and every single value is unique. So we already know that, I guess, but not every value, maybe every entry. So no two entries are the same, or just all entries are unique. Or else the decryption function could not possibly decrypt the ciphertext to a unique plain text. So what did I do this time? So I'm just trying to like go through the paper and see what I did. Because yeah, I just kind of cheated and took the ciphertext as being what the example proved to me should be the output. So I kind of just cheated. It's obviously 1, 2, 3, 4, whatever. I didn't like. Yeah, a bit confused, but it's all right. The key obviously can. Yeah, I need more. I need to watch more articles. All of the like tutorials I've gone through are showing relatively. I've only gone through a couple tutorials, so I can just go through more of them as we keep going through the book. But have gone through simple examples of how to use the library, but not necessarily like why it's doing what it does. And I think that's where the book is helping me more, is like, why is each step happening the way it has to happen? Not so much, okay, put this into this and it works this way, which is more high level and more like the research instead of the engineering. Okay, it's a big table. One, this is what mathematicians call a permutation. Okay, so it's simple enough. Permutation. I need to do more math work. Tuesdays and Thursdays as well, to be fair. It's a permutation. The table is merely a list of all possible elements where the order has been rearranged. A block cipher with a block size of k bits specifies a permutation on k bit values for each of the key values. Okay. So as a point of clarification, since it is often confused, a block cipher does not permute the bits of the input plaintext. Okay, so let's make sure we do understand this. Oh, so much happening. So my Ethereum protocol fellowship grant got approved. 4 equal monthly payments on the first of each month. The first payment will be automatically dispersed in November. I shouldn't read this out loud, maybe, I don't know. In order to receive future payments, you must continue participating. Verify your biweekly development in GitHub. In order to receive, I need to give a photo of my passport, as well as a recent utility bill, in a future email from the EF finance team. That's okay. I don't like that part of it, but I mean, I understand that's like the part of it. And I have to give my real name, which I don't like doing. I'm trying to change my legal name on my Canadian passport, but I have not done it yet. Anyways, I said I would do it this year, but it just hasn't happened. And so I need like mental space to do it, but one of those things. Okay. Okay, as a toy example. So I like examples. So example. If k equals 8. Oh, I should put the definition. So definition block cipher, a block cipher takes all the 2 to the k possible k bit inputs and maps each to a unique output, which seems straightforward from what we just went through. So let's see what they're trying to tell us to do. So if k equals 8, right, an input of, oh gosh, zeros, I'm going to do it, 00005671 might encrypt to 0, 1, 1, 2, 3, 4, 5, 6 under a given key, but it might also encrypt to 1101110 under a different key. I mean, this part's annoying, but depending on the design of the... So that last part is kind of annoying, depending on the design. Okay, so to me, it makes you want to look back here and go through this kind of aspect again. So what we're saying is a block cipher takes all 2 to the k possible k-bit inputs and maps each to a unique output. So this right now, we know we have unique inputs, right? If that's a plain text, and there's a unique output, right? Based on this key. And if you use the same key, to encrypt or decrypt a different key, so a different key would be like putting a 1 there, with the same ciphertext, should give you a different output. Now this should be relatively straightforward to show, because our output right here is we have our key, we have our plain text, we have our output, and now this should be very straightforward with cargo build, cargo run. So before we had a key of 0123, plain text of 0123, and this is our output 1820, right? And you change the key just by 1 digit, and not only do the first numbers change, which is I think the very important part, but all of the values are completely randomized once again. Like you would have had no clue. So everyone can have a key that's off by the tiniest little bit, and the output is completely randomized. You would never know what you changed based on the key to get you a different value. I am going to change this back to 0 because this is my little play my playroom here. So different types of attack. Given the definition of a block cipher, the definition of a this is good. The definition of a secure block cipher seems simple enough. It is a block cipher that keeps the plain text secret. Although this is certainly one of the requirements, it is not sufficient. This definition only requires that the block cipher be secured against ciphertext only attacks, in which the attacker gets to see only the ciphertext of a message. There are a few published attacks of this type, but they are rare against well-known and established block ciphers. Most published attacks are of the chosen plaintext type, which is a little bit weaker again than the chosen ciphertext type. All of these attack types apply to block ciphers. So So I guess all attack types from 2.6 pertain to block ciphers. Some are specific to them. Generally, is one that keeps the plain. Let's just keep trying to write it simply, right? Keeps P secret, but that is only sufficient to mitigate against plain text only. So to me, that's good enough for now. It shows us why the security definition is important and how we treat mitigating against plain text only attackers isn't good enough. We're here really trying to mitigate against all types of attack, but like we're going to dig into some specific ones that are more prevalent. The first one is the related key attack. So you have the related key attack. First introduced by Eli Beham. So I am going to put the name here just so we can pay homage. Eli Beham, 1993. A key-related attack assumes that the attacker has access to several encryption functions. These functions, let me just do this then. Attacker has access to several encryption functions. These functions all have an unknown key. Okay, so these functions all have an unknown key but share a relationship that the attacker knows. So you don't know the actual keys of these functions, but you know they share some kind of relationship with one another. This sounds very strange, but it turns out that this type of attack is useful against real systems. There are real-world systems that use different keys with a known relationship. At least one proprietary system changes the keys for every message by incrementing the key by 1. So key inc, plus inc by 1. That could be a reason why it would be known. Consecutive messages are therefore encrypted with consecutively numbered keys. It turns out that key relationships like this can be used to attack some block ciphers. Sorry, my coffee. There are even more esoteric attack types. When we designed the two-fish block cipher, we introduced the concept of a chosen key attack. Okay, so chosen key attack. And then I'll just put cute. Someone's coming and cleaning our yard. So two fish, right? That's where that kind of came from. In which the attacker specifies some part of the key and then performs a related key attack on the rest of the keys. So this is where, attacker specifies some part of the key, then performs related key attack. I think this happened in Ethereum or Bitcoin, where a website would allow you to make a wallet, but they would actually give you a random wallet, but they actually kind of, instead of giving you like 12 random words, so like having like 128 bits of security or whatever security you were supposed to have, they actually pre-planned or whatever, or had some predetermined words, like 6 of them are predetermined or whatever. So you could imagine, right, if you were, half the words, figuring out the other ones, you can brute force them more easily. And I think people actually lost a bit of money on that. So pretty interesting to understand how this kind of works in practice. If you're kind of rolling cryptography with less security than you thought you had, someone can brute force after that. So why would we even consider far-fetched attack types like related key attacks and chosen key attacks? We have several reasons. First, we have seen actual systems in which related key attacks are on the block cipher was possible, so these attacks are not that far-fetched at all. In fact, we have even seen standardized protocols that required implementations to key a block cipher with 2 related keys. One key K that is chosen at random, and another key K prime that is equal to K plus the fixed constant, which sounds like not a very efficient way to do that. Second, block ciphers are very useful building blocks, but as building blocks, they tend to get abused in every imaginable way. One standard technique of constructing a hash function from a block cipher is the Davies-Mayer construction. In a Davies-Mayer hash function, the attacker suddenly gets, let's just write it down. So in a Davies-Mayer hash, we're not going to go into it too deeply, but the attacker gets to choose the key of the block cipher, which sounds wild, right? Which allows related key and chosen key attack. So given like an example, because it actually happens in like a real, we talk about hash functions in chapter 5. We won't go into the details of the Davies-Mayer construction in this book. It's safe to say, however, that any definition of block cipher security that ignores these attack types or any other type is incomplete. So yeah, it's actually not, cannot be used to attack two fish, but anyways, they found the attack while working on two fish. Maybe I should just put like authors, so it's just like it's known. Maybe just be like working on two fish. And then I do kind of want to get a, let's just take a new one, Davies-Mayer. Oops. Let's keep it simple. I don't want to be too straightforward, complicated with it. I will just... Anyways, we'll go through it in chapter 5. So let's just go CH5, and then eventually I can just link it to chapter 5, and people can learn all about what's going on there. Oh yeah, they won't go into the book at all, actually. So maybe I should just go into like maybe they'll have just a specific. There you go. The Davies-Mayer single block length compression function feeds each block of the message as the key. Interesting. What? Each block of the message as the key to a block cipher. It feeds the previous hash value as the plain text to be encrypted. The output ciphertext is then XORed with the previous hash value to produce the next hash value. In the first round, when there's no previous hash value, it uses a constant, okay, in mathematical notation, HI equals encryption of message I with HI XORed HI minus 1, XORed with HI minus 1. The scheme has the rate, K in the key size, okay. If the block cipher uses, for instance, 256-bit keys, then each message block, message I, is a 256-bit chunk of the message. If the same block cipher uses a block size of 58 bits, the security... I won't go into all this right now, but what I will do is just link it because they're not going to talk about it in the book, and I'm not even sure if it's useful to go through because, again, this book was written 12 years ago, and I'm sure no one actually wants to use that right now, but it could be a good, extra learning resource for someone that wants to dig in. The block cipher is a module that should have a simple interface. The simplest interface is to ensure that it has all the properties that anyone could reasonably expect the block cipher to have. Allowing imperfections in the block cipher just adds a lot of complexity in the form of cross-dependencies to any system using the cipher. In short, we want to over-engineer our block ciphers for security. The challenge is to define the properties that one reasonably expects from a block challenge. Define the properties that one reasonably... I cannot spell today. Well, any other day, but still. Expects from a block cipher. Okay. 3.3. The ideal. I like this because it's kind of showing you that, like, any block cipher can arguably be ideal, but, like, how do you define it as ideal? And something that's ideal, I guess, for me would be secure, but, yeah. It is actually very hard to define what a block cipher is. It is something that you know when you see it, but can't quite define. The theoretical community has crystallized some of these properties into specific definitions, like pseudo-randomness and super pseudo-randomness. So I guess they have some definitions that we can go into. The block cipher community itself, however, uses a much broader definition covering things like weak keys and chosen key attacks. Here we take the approach of trying to help you understand what the block cipher primitives community believes a block cipher to be. We call this an ideal block cipher. So what the block cipher primitives So it isn't really anything except for what the block cipher community thinks it is, but we're kind of going away from specific definitions in theory into like practical definitions of the community. So what would the ideal block cipher look like? So what would the ideal block cipher look like? So this is interesting because, again, I think it's like timeless information where it doesn't matter like when you're building this. It should be a random permutation. Okay. Okay, simple enough. We should be more precise. So for each key value, the block cipher. Okay, that's honestly simple enough. It should be random permutation. That's quite specific. As we mentioned in section 3.1, you could think of a 128-bit block cipher as a huge lookup table with 2 to the 128 elements of 128 bits each, which is like so much, like it's crazy. The ideal block cipher consists of one of these tables for each key value, with each table chosen randomly from a set of all permutations. I think that's actually a pretty good example. So as in 3.1, you know, so a 128-bit block cipher, you know, is similar to, you know, lookup table of 2 to the 128 elements of 128 bits each. You know, so ideal block cipher, I think that's a pretty good definition as well, with like an example. Consists of one table for each key value, and then each table chosen randomly from the set of all possible permutations. So there's no way to like make the set smaller or anything. The choice should be random in that set. And yeah, it covers every single permutation. Strictly speaking, this definition of the ideal block cipher is incomplete, as the exact choice of the tables has not been specified. As soon as we specify the tables, however, the ideal cipher is fixed and no longer random. To formalize the definition, we cannot talk about a single ideal block cipher, but have to treat the ideal block cipher as a uniform probability distribution over the set of all. Okay, yeah, so this is, you know, not looking at one, you know, cipher, but treat the ideal block cipher as a uniform probability distribution over the set of all possible block ciphers. Anytime that you use the ideal block cipher, you will have to talk in terms of probabilities. This is a mathematician's delight, but the added complexity would make our explanations far more complicated. So we will keep the informal but simpler concept of a randomly chosen block cipher. We also stress that an ideal cipher is not something that can be obtained in practice. It's a probability, I guess, which is the idea. It is an abstract. This helped me as well to really understand that you can't really get an ideal block cipher, but it's something you talk about as a probability. And instead of going for this specific probability, you go for this average probability, and you know, it helps you understand how secure your system is. It is an abstract concept that is used when discussing security. Okay, let's actually scroll up on both of these. Definition of block cipher security. Okay, so I like when it gives a few definitions, so let's just take them both down. As noted above, there are formal definitions of security for block ciphers in the literature. For our purposes, we can use a simpler but informal definition. Definition 1. A secure block cipher is one for which no attack exists, which is obviously impossible. Definition 2. An attack on a block cipher is a non-generic method of distinguishing the block cipher from an ideal block cipher. So this is actually one of the things that I'm glad I'm writing down, but kind of confuses me. So let's put a space between these so my brain doesn't hurt. So a secure block cipher is one for which no attack exists. So we already know that doesn't exist. We already know that any block cipher could technically have an attack that exists that we don't know about yet. So together with the second definition, it's supposed to make more sense. So a block cipher, attack on a block cipher. So if you're actually attacking one, it's a non-generic method. So it's not like you're using the way it's supposed to be used. You find some new method of distinguishing the block cipher from an ideal one. So the ideal one does this, right? And so if you can somehow distinguish the block cipher from being away from ideal, then you have an attack. It's kind of like confusing in my opinion, putting it like that, but that's at least the definition they have, and we'll keep going and seeing how it clarifies things as we go. So what do we mean by distinguishing? Oh, this is like the best one. So what does it mean to distinguish a block cipher from an ideal block cipher? This is the part that always confused the heck out of me. Given a block cipher, so given a block cipher X, we compare it to an ideal block cipher with the same block size and the same key size. Okay, step 1. You have a block cipher and you compare it to an ideal block cipher with the same block size and the same key size. So a definition again, distinguisher is, it just doesn't like the fact that I wrote it out like that. So a distinguisher is an algo that is given a black box function that computes, okay, like whatever, fine, that computes the block cipher X or an ideal block cipher. Simple enough. A black box function is a function that can be evaluated, but the distinguisher algorithm does not know how the internal workings of the function in the black box. Both the encryption and decryption functions are available, and the distinguisher algorithm is free to choose any key for each of the encryptions and decryptions it performs. The distinguisher's task is to figure out whether the black box function implements the block cipher X or the ideal cipher. Ooh, interesting. So the distinguish, I already knew this, but doing it like, this thing, reading it again is always like fun, and like you just take it a different way, in my opinion. The distinguisher algo is free to choose any key for each of the encryptions and decryptions it performs. Oh, maybe I'm just spelling it right. It's just okay. So this algorithm can choose any key it wants. It can throw any value. The task, figure out whether the black box function, so this random function that the distinguisher algorithm is putting values into, and implements the block cipher X or the ideal cipher. Because remember, you shouldn't be able to tell whether it's the block cipher that you're using or it's some ideal cipher, because there should be complete randomness, arguably, and completely secure, and so you test against that. It doesn't have to be a perfect distinguisher as long as it provides the correct answer significantly more often than the wrong answer. Doesn't have, I mean, even, have to be perfect, just correct, greater than 50% or 2. It doesn't like that, eh? Like, does it like it better like that? No. I just don't think it's an appropriate place to use like 50%. Oh yeah, it doesn't like percents either. So greater than, simple enough. Doesn't the perfect is correct greater than half the time. Significantly more. Sure. Let's keep it simple then. There are, of course, generic and trivial solutions to this. We could encrypt the plaintext 0 with the key 0 and see if the result matches what we expect to get from block cipher X. This is a distinguisher, but to make it an attack, the distinguisher has to be non-generic. Okay. Choosing the plain text 0 and the key 0 is a distinguisher, but to make it an attack, the distinguisher must be non-generic. I think this is also another part where I was a bit confused, like non-generic and generic distinguishers. Sorry, distinguisher must be non-generic. This is where it becomes difficult to define block cipher security. We cannot formalize the notion of generic and non-generic. Again, this is kind of why I was getting a bit confused, because it says, oh, it just has to be generic, and then goes, oh. So it's a bit like obscenity. We know it when we see it. A distinguisher is generic, so I'm going to try this. If we can find a similar distinguisher for almost any block cipher. So the attack must be non-generic, and it's generic if it's similar for any block cipher. So we need to find a non-generic attack that's unique to this block cipher. So a distinguisher is generic if a similar distinguisher can be found for almost any block cipher. So it's not like unique in any way. I keep writing distinguisher. Okay. In the above case, the distinguisher is generic because we construct one just like it for any block cipher. This attack would even allow us to distinguish between two ideal block ciphers. Of course, there's no practical reason for one to distinguish between two ideal block ciphers. Rather, this attack is generic because we could use it to distinguish between two ideal block ciphers if we wanted to. The attack doesn't exploit any internal property of the block cipher itself. That's all kind of obvious based on like the two definitions, I guess. But we can also create a more advanced generic distinguisher. Encrypt the plaintext 0 with all the keys in the range from 1 to 2 to the 32, and count how often each value for the first 32 bits of the ciphertext occurs. Okay. Suppose we find that for a ciphertext X, for a cipher X, the value T occurs 5 times instead of the expected 1 time. Sure. This is a property that is unlikely to hold for the ideal cipher. Okay, obviously, right? Because you only want to show once and it's showing up 5 times, so it's not unique, okay? And would allow us to distinguish X from an ideal cipher. That makes sense. This is still a generic distinguisher. Ooh. Oh, because you're encrypting 0, you can do that for any block cipher, sorry. As we can easily construct something similar for any cipher X. It is in fact extremely unlikely that a cipher does not have a suitable value for T. So apparently if you do encrypt a plaintext 0 with all the keys, you would probably get some collisions anyways. This attack is generic. The way it is described, it is applicable for all block ciphers. It doesn't exploit a specific weakness in X. Such a distinguisher. Okay, things become more complicated if we design a distinguisher as followed. We make a list of 1,000 different statistics that we can compute about a cipher. We compute each of these for cipher X and build the distinguisher from the statistics that gives the most significant result. We expect to find a statistic with a significance level of about 1 in 1,000. We can of course apply the same technique and find distinguishers for any particular cipher. So this is a generic attack, but the generic nature now depends not only on the distinguisher itself, but also on how the distinguisher was found. I mean, I think it's just getting very general now and giving more examples, but maybe not. Okay. That's why nobody has been able to formalize a definition of generic attacks. Okay, well, I'll write that down. Nobody has been able to formalize a definition of generic attacks and block cipher security. So if you're still feeling confused at this point, don't worry, because no one's giving you a formal definition, and neither am I. We would love to give you a clean definition of block cipher security, but the cryptographic community does not know enough about cryptography to be able to do this in full generality. Instead, existing formal definitions often limit the capability of an attacker. For example, existing formal definitions might not allow chosen key attacks. While these assumptions can hold in some cases, we try to build block ciphers that are much stronger. Okay, so we try and build it as strong as we can, and there's no way to really formalize the definition here, I suppose. We must not forget to limit the amount of computation allowed in the distinguisher. We could have done this explicitly in the definition, but that would have complicated it even further. Okay, so you should limit. Okay, that's kind of. Anyways, if the block cipher has an explicit. Okay, yeah, I mean, must be sure to limit the amount of, or like, the computational power of the distinguisher, which is kind of like the attacker, like in a simulation, right? Distinguished. Why? If the block cipher has an explicit security level of n bits, then a successful distinguisher should be more efficient than an exhaustive search on n-bit values. If no explicit design strength is given, the design strength equals the key size. This formulation is rather roundabout for a reason. It is tempting to just say that the distinguisher has to work in less than 2 to the n steps. This is certainly true, but some types of distinguishers give you only a probabilistic result that is more like a partial key search. The attack would have a trade-off between the amount of work and the probability of distinguishing the cipher from an ideal cipher. For example, the exhaustive search I think it should be simple like this. So, okay. For example, an exhaustive search of half the keys in a space requires 2 to the n-1 work and provides the right answer 75% of the time. Oh gosh. An exhaustive search of half the key space requires less than half the work, right? So 2 to the power of n-1 work and provides the right answer 75% of the time. If the attacker finds the key, he knows the answer. Well, if he doesn't find the key, he has a 50% chance of guessing right by simply guessing at random. So it's kind of like a weird little thing, but either he gets it right or has 50% chance, so it's 75. So overall, the chances of getting the right answer are therefore 0.5 plus 0.5 times 0.5, which equals 75. I actually think it's cool. So if attacker doesn't, find key, or no, if attacker, Either attacker finds key or guesses with 50% probability. Okay. By comparing the distinguisher to such partial key space searches, we take this natural trade-off into account and stop such partial key searches from being classified as an attack. Okay, so that's interesting. But I'm not going to go too deep into that. It's relatively straightforward from the math and like just understanding how it's whatever. Our definition of block cipher security covers all possible forms of attack. Ciphertext only, known plain text, adaptively chosen plain text, related key, and all other types of attacks all implement a non-generic distinguisher. That is why we will use this informal definition in this book. It also captures the essence of professional paranoia that we talked about in Chapter 1. We want to capture anything that could possibly be considered a non-generic attack. So why spend multiple pages on defining what a secure block cipher is? This definition is very important because it defines a simple and clean interface between the block cipher and the rest of the system. This sort of modularization is a hallmark of good design. In security systems where complexity is one of our main enemies, good modularization is even more important than in most other areas. Once a block cipher satisfies a security definition, you can treat it as if it were an ideal cipher. After all, if it does not behave in an ideal cipher in the system, then you have found the distinguisher for your cipher, which means the cipher is not secure according to our definition. If you use a secure block cipher, you no longer have to remember any particularities or imperfections. I think that's important. If a secure block cipher is used, like why do we care? It is no longer necessary to remember any particularities or imperfections. The cipher will have all expected properties. I'm gonna finally finish my coffee. Now it's time to finish my smoothie. It's a bit warm now, but that's all right. All expected properties. This makes the design of larger systems easier, which is the goal, hopefully, of what I'll be doing in the future. Of course, some ciphers that don't meet our stringent definition might be good enough in practice for a specific application as currently defined, but why take the risk? Even if the weaknesses of a particular block cipher under our definition are highly theoretical, such as requiring an unrealistic amount of work to exploit and thus not being very vulnerable to compromise in practice, a block cipher that meets the definition is much more attractive. Yeah, we're not even going to go through other types of things, but we will have to now 3.4.1 parity of permutation. Now, this is pretty cool and pretty confusing in my opinion, but I learned a lot about this, and one of the chapter questions actually wants you to write a program that the complementation property holds, which is pretty cool. So not my cup of tea, but we'll at least start writing notes about it and digging in. I have half an hour more. It's probably like 15 minutes of actual Note taking. I guess I hope just to get through this one section, and then I'll just like stop and go stretch my legs, get ready for my next meeting, and yeah, should be fun though. Okay, so unfortunately we have one more complication. As we discussed in section 3.1, encryption under a single key corresponds to a lookup in a permutation table. Think about the constructing this table in two steps. First, you initialize the table with the identity mapping by giving the element at index I the value I. Then you create the permutation that you want by repeatedly swapping two elements in the table. It turns out there are two types of permutations. Those that can be constructed from an even number of swaps, called even permutations. So it turns out there are two types of permutations. Those that can be constructed from an even number of swaps, and those that can be constructed from an odd number of swaps, even in odd permutations. It should not surprise you that half of all permutations are even and half of all permutations are odd. Most modern block ciphers have I don't know if this is still correct, so I'll put an asterisk here as well. So most modern block ciphers have a 128-bit block size, but they operate on 32-bit words. So obviously there needs to be padding or some way to make sure that these words are all, the 128-bit block size. Okay. I'll just put an asterisk at the very beginning, so it's clear that, hey, oh gosh, no, it wants to. I'll put an asterisk here. They build the encryption function from many 32-bit operations. So and computers work well with 32-bit operations, so that's probably why. We now have some computers that work in 64-bit architecture, but yeah, operations. This has proved to be a very successful method, but has one side effect. It is rather hard to build an odd permutation from small operations. As a result, virtually all block ciphers only generate even permutations. Now, hopefully this kind of makes sense. If you're taking a bunch of multiple, like 32 bits, and bringing them together, if you have an even number of them, because you're going to have like 4, right? It's going to be difficult. If you multiply things by themselves, you get even. If you multiply two negatives, you get even. So getting odd is more difficult. So yeah, it is, I guess, rather hard or harder. Harder to build an odd permutation from small op. I think that's the idea. The idea is that you're trying to do small operations to verify things quickly. You could still do it. It will just take larger operations. There's no point. Operations as a result, almost all block ciphers only generate even permutations. Just like answers to like a lookup table, I guess. This gives us a simple distinguisher for nearly any block cipher, one which we call the parity attack. So we'll try and then define parity attack. Okay, for a given key, extract the permutation by encrypting all possible plain text. So again, like this is not necessarily possible for like a huge like encryption scheme, but let's say it was much smaller. Yeah, you encrypt them all. If the permutation is odd, we know that we have an ideal block cipher. Because the real block cipher never generates an odd permutation. So if you're checking the block cipher X against the ideal block cipher, you just put as many plaintext as you can in, or all plaintext in, and whenever you're checking the distinguisher, whenever the distinguisher is checking the algorithm, it'll be right 75% of the time. Remember, we said it's a distinguisher if it's right more than half the time. So let's just call it parity attack. For a given key, extract permutation by encrypting all possible plain text. You know, if odd, then you know you've attacked. We know it's an ideal block cipher. Most ciphers only produce even permutations. Hopefully that's very clear, right? If even you claim to have the real cipher, attacker claims to have the real block cipher, and we already know, and is correct 75% of the time, which is way more than it's wrong. So we know that that's an attack. Okay, it will produce the wrong answer only if it is given an ideal cipher that produces an even permutation. The success rate can be improved by repeating the work for other key values. This attack has no practical significance whatsoever. To find the parity of a permutation, you have to compute all but one of the plaintext ciphertext pairs in the encryption function. Okay, so, and this is very clear. So no practical significance to the attack. Why? Because attacker would have to compute all but one of the plain text cipher text pairs. Whoops. Pairs of the encryption function. Okay, so there's no practical attack. The attacker would have to compute all but one of the plain pairs of the function. The sole remaining plain text maps to the sole remaining. And then, yeah, when you get to this point, you've already broken the cryptography. Like, you should never never allow that many plain text cipher text in a real system. So this is a known attack for every single system in production necessarily. But let's say you have billions and billions of possible keys. Don't let someone make billions and billions and billions of queries. But even then, it wouldn't be that useful, probably. You know, and then other types of attacks would hurt much sooner. You know, in this case, other types of attacks would hurt much sooner anyway, so don't do that. In particular, once the attacker knows most of the plain text ciphertext pairs, he no longer needs a key to decrypt the message, but can simply use a lookup table created from those pairs. So like in particular, once the attacker knows most of the plain text ciphertext pairs, they no longer need a key to decrypt messages, but can simply use a look table created from those pairs. Decrypt. Okay. We have one more definition and we are done. We could declare the parity attack to be generic by definition, but that seems disingenuous, since the even parity of block ciphers is a peculiar artifact of their designs. Rather, we prefer to change the definition of the ideal block cipher and limit it to randomly chosen even permutations. So we will go back to the top. We will add a third. Oh, didn't I put the definition somewhere? I'll put it right here. Oops. Definition 3. Yes, it likes me. An ideal block cipher implements an independently chosen random even permutation for each of the key values. So we're honestly just changing the definition to say, hey, you know what? In the ideal block cipher, we're only dealing with even stuff anyways. So, try and distinguish between that only for even values. Independently chosen. Why can I not type? That's okay. Okay. It is a pity to complicate our ideal cipher this way, but the only alternative is to disqualify nearly all known block ciphers. For the overwhelming majority of applications, the restriction to even permutations is insignificant. As long as we never allow all plain text ciphertext pairs to be computed, even in odd permutations are indistinguishable. If you ever have a block cipher that can generate odd permutations, you should revert to the original definition of the ideal block cipher. In practice, parity attacks have more effect on the formal definition of security than on real-world systems. So you can probably forget about this whole issue of parity. The discussion also serves as another example of how cryptographers think. It is more important to exhibit professional paranoia and consider a superset of realistic attacks and then pair away the unrealistic ones than to start with only realistic attacks and then find new ones. So I'll just put that there in the den. Just as like a way to end it off. It is more important to exhibit professional paranoia and consider a superset of realistic attacks and then pair away the unrealistic ones and to start with only realistic attacks and try to find new ones. Let's add superset. We'll need that, I'm sure. Oh. Okay. Okay, so now we get into real block ciphers, which I'll go through on Monday at this point. This weekend, I'm probably going to focus on like math, implementing cryptography in Rust, like watching more videos on that and stuff. Monday, I'll try and finish off chapter 3 and hopefully try and get some of the homework problems. For this real block ciphers, it's kind of just an overview of each of these systems. So it's a kind of an overview, and then it goes through DES, which is quite long. It goes through AES, and then it goes through like Serpent, Twofish, other AES finalists, what key size to use, and exercises. So I haven't even gone through all of chapter 3 yet. I definitely have not gone through all the exercises. I'm excited to kind of go through and read more. But yeah, that's where we're at. We're at 3.5 real block ciphers, and we'll get to that on Monday. So toodles all. I'm going to finish my smoothie.